All right, in section 1.13, we're going to be discussing removing discontinuities. So this is just really a category of problem from the AP exam that's very common, so we kind of devote our own section to it. So no definitions, you know what a discontinuity is, you specifically know what a removable discontinuity is. So it's going to be problems similar to this one. We're going to jump right into an example. This says, for what value of the constant c is the function f continuous on the interval negative infinity to infinity? So all real numbers. So the first thing we need to notice is that this is a piecewise function, but each piece separately is polynomial. And polynomials are continuous everywhere. So the only location that we need to be worried about a possible discontinuity is where the function is being pieced together, right, at 2. We just want to make sure it maintains continuity there. So to do that, we're going to use our definition of continuity, right? The limit as x approaches a for the function equals f of a. And remember that implicitly, if that limit exists, what we're saying is that the limit as x approaches a from the left is equal to the limit as x approaches a from the right. And so that's what we need to check, but just at this one point at x equals 2. So let's get started there. The first thing I'll do is look at the limit as x approaches 2 from the left of my function. And for that, if we want to approach 2 from the left, that's values that are less than 2. So I'm going to be using the top piece of my function. Right? And to evaluate a one-sided limit, we can still just do a direct substitution. So I'm just plugging in 2 for x. So that's going to give me, what? C times 2 squared plus 2 times 2. So that's 4c plus 4. Great. And so next I want to take a look at the limit as x approaches 2 from the right. So the piece of my function that I'm going to look at there is the bottom piece, because if we're approaching 2 from the right, we're using values that are larger than 2 but approaching 2. And again, I'll just make a direct substitution, but now I'm substituting into that bottom piece. So I'm going to get 2 cubed plus, or no, minus 2c. So we get 8 minus 2c. All right, well, for the overall limit, you need the left-hand limit and the right-hand limit to be the same. So we're just going to set those equal to each other. So 4c plus 4 is 8 minus 2c. And now we can just solve for c. So let's see, I'm going to add 2c to both sides. Gets me 6c, subtract 4 from both sides, gets me 4. C equals 4 over 6, which is 2/3. And so this is going to be my claim, that c equals 2/3 will make that function continuous at those points. So let's see, we can do a little visual check in GeoGebra. See if I got the right value for c. So I'm going to go function. Let's see, the top piece would be 2/3 x squared plus 2x. That's when x is less than 2, so I'll just make it like 999 up to 2. Okay. There's that piece. And then the bottom piece is going to be x to the third minus 2 thirds x, and we'll go from 2 to, and there's g. So you can see that, yep, even though it's a piecewise function, we are connecting at 2. And so to go back to the example to verify that, all right, so what we had was 2 thirds x squared plus 2x, and then down here we had x cubed minus 2 thirds x. So if we actually plug in f of 2, we should be using the bottom piece for that, because that is where it includes 2. So it gets 2 to the third minus 2 thirds times 2, just 8 minus 4 thirds, which is 24 over 3 minus 4 thirds, 20 over 3. And so we end up with that same thing as our right hand and our left hand limit as well. All right, let's try another one. Same idea. Let f be the function defined above where a is constant. For what values of a, if any, is f continuous at 3? So this is the same approach. They're only asking us, though, for continuity at 3. So we just need to look at the limit as x approaches 3 from the left. Oops. There we go. Of f of x. And approaching 3 from the left, I'm using this top piece. And I'm just going to do direct substitution of 3 for x. So I'll get a squared plus 3 squared, which is a squared plus 9. And then I'll do the same thing, but now from the right. And for that one, I'm going to use the bottom piece. We're approaching 3 from the right, so from larger values of 3. And I'm going to do a direct substitution again, so I'm going to get a times 3 plus 3, or 6a. Now we just need to set those two equal to each other. So a squared plus 9 equals 6a. It's quadratic. We can solve this one by factoring. So I'll just move the 6a to the other side, get it equal to 0, and realize that that's a minus 3 squared. So we get a equals 3. And so this is the value that we would expect it to make this function continuous at 3. So the function then becomes f of x equals, going to be what, 9 plus x squared when x is less than 3. And let's see, 3 times x plus 3 when x is greater than or equal to 3. And you can see if you plug in 3 to the top, you're going to get 9 plus 9, 18. Plug in 3 to the bottom, you're going to get 3 times 6, also 18. And so now we have the case that the limit as x approaches 3 of f of x equals f of 3, which is 18. And so it checks out. It is continuous, but the answer is just a equals 3. All right. Let f be the function defined above where c is a constant. For what value of c is f continuous for all x? So again, right away, we're going to see this is a piecewise function. The top piece is a trig function, which is continuous everywhere. The bottom piece, you probably haven't dealt with these in a while, is natural log, which is continuous from 0 to infinity. And so what we're going to be concerned about is just what's going on at where these functions are being pieced together. So again, same approach. In this case, we're going to be looking at -1 and making sure the limit as x approaches -1 from the left is the same as that limit from the right. From the left, we're going to use the top piece of that function. You can just do a direct substitution. And so I would get 4 minus cosine of -1. And we'll just leave it as is for now, because cosine of -1 I don't think is going to come out to be a nice looking number. So we'll probably be using our calculators to solve this equation. All right, the limit as x approaches -1 from the right, we then use that bottom piece, and I'll do a direct substitution there, so I'll get c plus 5 times the natural log of -1 plus c. All right, and now I need the limit from the left to equal the limit from the right. So we're going to create an equation. 4 cosine of -1 has to equal c plus 5 natural log of -1 plus c. And yeah, so this would be like something they would throw at you on the calculator portion of the exam. So let me open my calculator and we'll review how to solve an equation in your calculator. Okay, so there are a couple ways you can do this in your calculator. One way to do it, we can go into our graphs, our y equals, and we can enter the equations separately. So you would just put the left-hand side of the equation in y1. Oh, sorry, that should be 4 minus cosine. Put the right side in y2, so I'm going to do x plus 5 natural log -1 plus x. And I'll do zoom 6, we'll start there. Great. So we can clearly see there's a point of intersection, and that's what we want to find. That's going to be the solution to our equation. So we can go into the the calc menu, and we just want to calculate the intersect. And I'll ask you for the first curve, and then I'll ask you for the second curve. Just make sure that your cursor is close to that point of intersection. So use the arrow keys to scroll until you can see it's close to that point of intersection. And then I'll ask you to guess. You don't really, in this case, need to do anything, but generally, if there are more than one point of intersection, you want to move the cursor close to the one that you want the calculator to find. Hit enter one more time, and there we go. So that is going to be our answer. C equals, I'm going to round it to 3 decimal places, so 2.269. And that is the value that will make our function continuous. That's it. All right, I got one more for you. Just another type of example, and it asks, for what value of x does f have a removable discontinuity? So just remember to find removable discontinuities. This is when you have common factors in the numerator and denominator that involve your variable, which means we just have to practice factoring. So notice in the numerator we can factor out a 2, and I'd be left with x squared plus 7x minus 8. In the denominator I have a quadratic that looks factorable, So we want to think about, okay, so what multiplies to 8 and adds to -9? So -1 minus 8. Oh, geez, my Apple Pencil just desynced. There we go. Okay, and same idea for the numerator. We now have a quadratic up there that we should be able to factor into two common factors. What multiplies to -8 and adds to +7, that would be +8 minus 1. So we note that we have a common factor of x minus 1. So set that equal to 0. And at x equals 1, we have a removable discontinuity. Now, from this factor, we do get an asymptote, but that's called an essential discontinuity or an infinite discontinuity. And this only specifically asks for the values of x that give us a removable discontinuity. So we don't need to say anything about what's going on at x equals 8. There's only a removable discontinuity at x equals 1. All right, here's your student example, similar to some of the ones that we did earlier. Go ahead and give it a shot and find the value of c for which that makes f continuous at all x, and we'll go over it in the next class.